Today we will solve the problem 4.33 of Griffith third edition, Introduction to Quantum Mechanics. The problem 4.33 is construct the matrix S sub R representing the component of spin angular momentum along an arbitrary direction r cat. Use a spherical coordinate for which r cat is equal to sine theta cos pi I cat, that is along x direction, sine theta sine pi j cat along y direction, plus cos theta k cat along z direction. Find the eigenvalues and normalized eigenspinors, that is spinors of SR. Answer is given. Don't worry about this right now. But you need not have the same answer. You can have same answer but a different phase vector. It need not be the same phase vector. That is this exponential term. We are going to see it. The spin angular momentum along r direction is equal to, by definition, S dot r dot product. Uh, Here S is a Sx, Sy, Hz. That is spin matrices along x, y, z direction. So Sx multiplied by the component along x direction. That is sine theta cos pi, and along y direction Sy, sine theta sine pi, sine theta sine pi, and along z direction cos theta, sz cos theta. Now you know the spin matrices, that is Sx is equal to this one, h cross pi 2, 0 1 1 0. Similarly, what about Sy, h cross pi 2, 0 minus I 0. Similarly, Sz is equal to this one. That is h cross over 2, 1 0 0 minus 1. Of course, we have here cos theta, here sin theta sin pi, here sin theta cos pi. So, using this, we will move further. Now we got this expression. We have three matrices. We will make it one. Here you have h cross over 2, h cross over 2 in all three parameter, all three terms. H cross over 2, h cross over 2. You take h cross over 2 as a common, then you multiply this matrix by sin theta cos pi. If you do the multiplication, this will be 0, and sin theta cos pi. Here also you have 1. So this will become sin theta cos pi. Here you have 0. Similarly, you come over here 0. Then you have minus I sin theta sin pi. Here plus I sin theta sin pi. Here you have cos theta 0. Then 0, here 0 minus cos theta. Of course, we have taken h cross over 2 outside. Now you add all three matrices. Here you have 0, 0 plus cos theta. So you will get cos theta here. And here sin theta cos pi, you add this minus I sin theta sin pi. So sin theta cos pi minus I sin theta cos pi. Here it is 0, so don't worry about this. Then you add these three. That is sin theta cos pi plus I sin theta sin pi. Sin theta cos pi, first this term, and I sin theta sin pi. This is 0, so don't worry about it. Then next this term 0 plus 0 minus cos theta. So you will get here cos theta. So now we got the single matrix. Uh, Here, so finally we got this. Here you can take sin theta as common. That is second row, first column. Here also sin theta. So you take sin theta outside, then you will have cos pi plus I sin pi. What about this term? You take sin theta outside, sin theta. Then you will get cos pi here minus I sin pi. So this is the angular momentum matrix along the direction R. Then we will move on further. Now we got S sub R matrix is equal to H cross over 2 cos theta sin theta cos pi minus I sin pi and sin theta cos pi plus I sin pi minus cos theta. This is the terms inside the bracket, that is cos pi minus I sin pi is equal to e power minus I pi. You know, if you expand this, you will get this. Similarly, here cos pi plus I sin pi is equal to e power plus I pi. So now this SR matrices reduces to H cross over 2 cos theta, then this e power minus I pi sin theta, and here you have e power plus I pi sin theta and minus cos theta. You bring H cross pi 2 inside the matrices, inside the matrix, and in order to find the eigenvalue lambda, you form a characteristic matrix. So here the first row, first column is H cross over 2 cos theta. Then you subtract the diagonal element by minus lambda. Subtract by the value lambda. Lambda is eigenfunction. Similarly, if you multiply this, you will get H cross over 2 e power minus I pi sin theta. Then here H cross over 2 e power plus I pi sin theta. And this, since this is the diagonal element, you multiply this minus H cross over 2 cos theta minus lambda because it's a characteristic matrix. If you multiply this and this, what you will get minus because there is an anti sign minus h cross squared over 4 and cos theta is cos squared theta and minus lambda is plus lambda squared. Then you multiply this and this. I will use a different color, that is uh, this term and this. Here, if you multiply e power minus I pi with e power plus I pi with e power minus I pi, you will get 1. Only remaining term is here h cross over 2 sin theta. Here also h cross over 2 sin theta, which is equal to minus because here uh, if you take a product of this matrix, you will get the negative sign naturally. So h cross squared over 4 sine squared theta because exponential term will become 1. So which is equal to 0 due to this characteristic matrix. Then we will solve this. Here we got this expression. Uh, you bring this term and first term and last term to the right hand side. So this minus will become plus, and left hand side you have left with lambda square. So in the right hand side you have here h cross squared over 4, here also h cross squared over 4, and you can take out h cross squared over 4 outside. Then here you have cos squared theta, here sin squared theta. You know very well the cos squared theta plus sin squared theta is equal to 1. So lambda square is equal to h cross squared over 4. So what about lambda? Lambda, if you take square root, you will get plus or minus h cross over 2, what we have expected from the Pauli spin matrices. So spin eigenvalue is plus or minus h cross over 2. Now you take SR matrix, S sub R matrix. That is angular momentum matrix at arbitrary direction R. You multiply with alpha and alpha beta column matrix. Here alpha is a spin up matrix, beta is a spin down. Sorry, alpha is a spin up state, beta is a spin down. Here also. Here this plus or minus h cross over 2 is lambda eigenvalue. So this must be equal to lambda times this spin up state and spin down state. So based on this understanding, we will move further. Now we got this relation. Here you can see both right hand side and left hand side you have h cross over 2. So you can cancel it, h cross over 2. Of course, there is plus or minus here. So this SR matrix multiplied by alpha beta column matrix, which is equal to plus or minus alpha beta column matrix. Now you can take the first row and you multiply this. You can take a second row also. You will get same result. I will guarantee that you will get same result. But I am taking the first row and I am multiplying this column. So which is equal to alpha because I am multiplying first row. So alpha times this cos theta plus beta times this e power minus I pi sin theta is equal to this plus or minus alpha. If you take second row, then it will be equated to beta. So you will get same result. No worry about it. So now what I am going to do is I am going to take this alpha term one side. Here you have alpha cos theta, here plus or minus alpha. So you bring this alpha cos theta to the other side. So naturally what will happen? You will get beta e power minus I pi sin theta. When this cos theta comes here, you will get minus cos theta. This is plus or minus 1 minus cos theta into alpha. Now what is beta? Beta is equal to, if you bring this exponential term to the other side, this minus will become plus, and this sin theta plus or minus 1 minus cos theta divided by sin theta. Here you have alpha. Then we will see what will happen next. Now we got this expression beta equal to this. Now here you have plus or minus 1. Take upper sign, that is plus sign. This one as plus 1. What will happen? You will get to beta equal to e power I pi 1 because we are taking plus 1 minus cos theta over sin theta into alpha. So you take e power I pi as it is. 1 minus cos theta from trigonometry relation, this is 2 times sin squared theta by 2. Similarly, sin theta can be written as 2 sin theta over 2 multiplied by cos theta over 2. Here you can cancel this 2 and this 2. And this sin theta by 2 get cancelled with this sin theta over 2. So this square will get cancelled. Now you have e power plus I pi. Here in the numerator you have sin theta over 2. Of course you have alpha also. Divided by, here you have only in the denominator cos theta over 2. This relation we are going to use later. So I am taking this as beta equal to e power I pi sin theta over 2 over cos theta over 2 alpha. Now you normalize the value of alpha and beta as requested in the problem. We are going to normalize this. That is, modulus alpha squared plus modulus beta squared must be equal to 1. So this can be written as modulus alpha squared. Then if you take modulus of beta squared, so if you take modulus, e power I pi into e power minus I pi will become 1. Then you square it, sin squared theta by 2 over cos squared theta by 2, and this modulus alpha squared. Now we can simplify this. That is, this term is equal to 1. Alpha modulus alpha squared sine squared theta by 2 over cos squared theta by 2 modulus alpha squared. This plus this is equal to 1. That is alpha squared plus modulus beta squared is equal to 1. Now we will move further. So now we got this expression, that is modulus alpha squared plus modulus beta squared. This is the beta squared. Just now we have seen modulus beta squared. So what I am going to do is I will take cos squared theta over 2 as common LCM here in the denominator. Then naturally we have to multiply the first term by cos squared theta by theta over 2. So alpha squared you have here as well as here, you take alpha squared modulus alpha squared. Then in the first term you are multiplying by cos squared theta over 2 plus here already you have sine squared theta over 2. So this terms inside the bracket is equal to 1. This will be 1. So for normalization condition, modulus alpha squared plus modulus beta squared is equal to 1. So this expression, because this terms inside the bracket is 1, you will get simply the numerator modulus alpha squared over this cos squared theta squared, which is equal to 1. So naturally, if we take alpha is equal to cos theta by 2. So now we got this relation beta equal to e power minus pi sine theta over 2 over divided by cos theta over 2 alpha. So just now we have seen this relation. So here alpha is equal to this one cos theta by 2. So this cos theta by 2 will get cancelled with this cos theta by 2 in the denominator. So beta is equal to e power I pi is sine theta over 2. So now what is the normalized spinor matrix? That is chi sub plus at any random arbitrary direction R is equal to alpha over beta. So here alpha is cos theta by 2 and beta is equal to this one e power I pi is sine theta over 2. Then we have to see for spinner down, that is chi minus. Then we will see it now. Now we got this relation, already we got this relation beta equal to e power I pi plus or minus 1 minus cos theta over sin theta times alpha. So earlier case we have seen the upper sign, that is positive. Now you can take the lower sign, that is minus. So minus 1 minus cos theta, numerator will come minus 1 minus cos theta. You take minus outside. Then this will become 1 plus cos theta. Now, from trigonometry relation, 1 plus cos theta is equal to 2 times cos squared theta over 2. And similarly, already we have taken sin theta equal to 2 sin theta over 2 into cos theta over 2. Now, here this term will get cancelled. This cos theta by 2 will get cancelled with this square. So and also this 2 and 2 will get cancelled. Now beta is equal to, you have negative sign here, minus e power I pi cos theta over 2 cos theta over 2 divided by sin theta over 2 times alpha. So as usual, as we have done earlier, you normalize this. That is modulus alpha squared plus modulus beta squared is equal to 1. Here, modulus alpha squared is equal to modulus alpha squared, modulus beta squared. this sign minus sign will become plus if you are taking modulus of it, and this exponential term also will become 1. So naturally you will have cos squared theta over 2 uh, divided by sine squared theta over 2 and this modulus alpha squared. Now we will simplify further. Now we got this relation, that is modulus alpha squared plus cos squared theta over 2 divided by sine squared theta over 2 multiplied by alpha modulus alpha squared, which is equal to 1. Here, as done earlier, I am taking sine squared theta over 2 as a common parameter. So you have to multiply the first term by sine squared theta over 2. So this modulus alpha squared, you have modulus of alpha squared here as well as here. So you can take modulus alpha squared as a common parameter. Then you have sine squared theta over 2 and cos squared theta over 2 plus cos squared theta over 2. So this terms inside the bracket will become 1. So this can be written, that is modulus alpha squared, because this term is 1, modulus alpha squared over sine squared uh, theta over 2 is equal to 1. Or from this we can find that alpha is equal to sine theta over 2. We have seen just now beta equal to minus e power I pi cos theta over 2 divided by sin theta over 2 multiplied by alpha. Here you replace alpha by is sin theta over 2. So this sin theta over 2, this sin theta over 2 will get cancelled. You will get minus e power I pi cos theta over 2. So spinor matrix spin down particle is this R indicate random direction is equal to alpha. Here alpha is equal to sin theta over 2 and beta equal to this one minus e power I pi cos theta. This is slightly different. Phase vector is different from the one which is given in the answer. So you have to multiply, that is multiply this by e power minus I pi, and here also multiply this e power I pi. This is after all a phase factor. Just changing the phase factor, your result will not change. That is you make it sure. So the first term will become e power minus I pi sin theta over 2. The second term, if we multiply e power I pi plus I pi into e power minus I pi is equal to 1. So this will become cos theta over 2. What it is given, exactly given in book, sorry, in the problem exam. So spinor matrix is for down spin, that is equal to e power I pi column matrix e power I pi minus I pi sin theta over 2 minus cos theta over pi. Subscribe to my channel to get my latest videos, and join my channel to support its growth and enjoy the exclusive perks. Also use the thanks button to make one-time contribution and support my channel. Thank you very much.